Hello and welcome. Today, we're going to dive into the invisible world that makes up, well, everything around us. We're going to see how something like a solid block of ice and a simple cup of tea are actually governed by the very same hidden rules. And, believe it or not, it all starts with a pretty simple question. You know the feeling, right? You stir a spoonful of sugar into your drink and poof, it just vanishes. But if you try the exact same thing with sand, all you get is gritty, cloudy water. So what gives? The difference seems huge, but the explanation, well, it's incredibly small. And that's the secret. Everything. I mean, the chair you're sitting on, the air you're breathing, even you, is made up of countless tiny particles, and they are all in constant, frantic motion. Understanding this one core idea, the particle theory, is really the key that unlocks everything else we're about to explore. Okay, so if everything is made of the same basic stuff, these particles, then why do we have such different states of matter? Why is ice hard and steam invisible? It all comes down to how those particles are arranged and, maybe most importantly, how much energy they've got. You can really think of this table as a story all about energy. Look at a solid. The particles have the lowest energy, so they're locked into this neat, regular pattern. All they can do is just kind of vibrate in place. But add some energy and you get a liquid. The particles break free and start sliding past one another, which is why liquids can flow and take the shape of whatever you put them in. Now pump in the most energy, and bam, you get a gas, with particles flying around like crazy with no fixed shape or volume at all. It really is all about the energy. So, since energy is the master controller here, what happens when we start messing with it, adding or removing it on purpose? Well, the particles begin this kind of dance, changing their formation and allowing matter to totally transform from one state to another. Let's start with the pair we all know best. When you add heat to a solid, like an ice cube, its particles soak up that energy and start vibrating faster and faster and faster until they literally break out of their fixed positions. We call that melting. The reverse, of course, is when you take heat away. The liquid particles slow right down, lose their energy, and lock back into that rigid structure. And that, of course, is freezing. And it's the exact same logic going from a liquid to a gas. You add enough heat to water, and its particles gain so much energy they just escape the liquid completely and fly off as steam. That's boiling. And you know when you see that steam fog up a cold mirror? You're literally watching condensation in action. Those high-energy gas particles are hitting that cool surface, losing all their energy, and clumping right back together into liquid water. And here's where things get really cool. Sometimes matter just skips the liquid phase entirely. Take dry ice, for example. That's just solid carbon dioxide, and it turns directly into a gas, a process we call sublimation. The opposite, which you see when frost forms on a cold window, is when a gas like water vapor turns directly into solid ice crystals. That's called deposition. It always comes back to that particle energy. All right, so I know what you might be thinking. This all sounds like a really neat theory, but we're talking about a world we can't even see. How can we be so sure it's actually real? Well, scientists have come up with some truly clever experiments that let us see the undeniable effects of these particles in action. Okay, picture this classic experiment. You take a tiny purple crystal, that's our solute, and you drop it into a beaker of water, our solvent, and you don't stir it, you just watch. All on its own, that purple color starts to spread out. What you're seeing is the solute particles and the water particles all moving around randomly, just bumping into each other over and over until they're perfectly mixed. It's visible, undeniable proof of that invisible particle movement. It gets even more elegant when you do it with gases. In this setup, you have cotton swabs, one soaked in ammonia and the other in hydrogen chloride, at opposite ends of a sealed tube. Where those two gases meet, they react and form a cool white ring of solid stuff. But here's the kicker. The ring doesn't form in the middle. It's way closer to the heavier hydrogen chloride end. And that's amazing proof not just that particles move, but that lighter particles, like ammonia, have to move way, way faster than heavier ones. So we've established that particles exist, they're always on the move, and they can mix together. Let's bring this full circle, right back to our original question about sugar in tea. This process of mixing at the particle level is what we call dissolving, and it's how we create something called a solution. First up, you've got your solvent. This is the liquid that does the heavy lifting. You can kind of think of it as the solver in the situation. In our cup of tea, the hot water is the solvent. And water is so good at this, it's often called the universal solvent because it can dissolve so many different things. Then you have the solute.
This is the substance that gets pulled apart and dissolved by the solvent. So in our tea, the sugar is the solute. When you add salt to water to cook pasta, the salt is the solute. It's the ingredient being mixed in.
And when those solute particles spread out perfectly and evenly among all the solvent particles, you get a solution. This is a special kind of mixture that's the same all the way through, what scientists call a homogeneous mixture. That perfect uniformity is exactly why you can't see the individual sugar crystals in your tea anymore.
But there's always a limit, right? Have you ever added so much sugar to your iced tea that a pile just sits at the bottom no matter how much you stir? When that happens, you've officially hit the limit. You've created a saturated solution. Basically, every single solvent particle is already busy holding on to a solute particle, and there's just no more room at the end. Now, this idea of a limit is what separates different substances. Salt has one limit in water, sugar has a completely different one, and the science of precisely measuring that limit is what we call solubility. It's how we turn this everyday observation into hard data. So here's the formal scientific definition. Solubility is the absolute maximum mass of a solute that can dissolve in a standard amount, 100 grams of a solvent. And that last part is absolutely crucial. It's always measured at a specific temperature. We have to lock in the temperature because, as we've already seen, changing it changes everything about how particles behave. To make this super concrete, let's just look at regular table salt. At about room temperature, so 25 degrees Celsius, you can dissolve exactly 36 grams of salt into 100 grams of water, not a tiny bit more. If you try to add a 37th gram, it's just going to sink right to the bottom. That number, 36 grams, is its solubility. And how do scientists figure this number out? Well, it's actually a pretty neat lab process. They'll usually dissolve a bunch of solute in hot water to make sure it's saturated, and then they'll let it cool down very, very carefully. The exact moment they see the first crystals start to reappear, they check the temperature. That's the saturation point. They just repeat this over and over to map out the solubility across a whole range of temperatures. And all that data gets plotted onto a graph called a solubility curve. You can basically think of this as a cheat sheet for a chemist. With just a quick glance, it tells you exactly how much stuff can dissolve at any given temperature. You can instantly see if a solution is saturated or if it has room for more. It's the one tool that visually connects everything we've talked about: particles, energy, temperature, and the absolute limits of dissolving. So we've pretty much established a rule, right? For most solids, if you heat them up, you can dissolve more. Simple enough. But what if you could cheat? What happens if you make a hot, perfectly saturated solution packed to the absolute brim with solute, and then you cool it down so slowly and so gently that those particles never get the signal to reform into crystals? What kind of unstable, super stuffed state would you create then?